Alright, today class we're going over how to solve physics words problems. So now we're getting into word problems, so this will be pertinent to now, but it's going to pretty much be how you're going to solve word problems the rest of the year. Yes, there will be plenty of word problems the rest of the year. So number one may seem obvious, but it makes it that much more important, is read the whole problem. Don't read half of it, read the whole problem. A small caveat on this is this would be a good time for you to maybe underline information you think is important or highlight. So just things that you think may be important to your problem solving in the future. And I shorten information to info because I'm lazy and I don't want to write the whole word. 2. Draw and label the problem. So you try to give yourself a visual of what's actually happening in this problem, not just the words. Get a nice picture, and then tell yourself what's happening, as in label it. 3 is make a list of all the variables you see. Variables and also the numbers. It's not a hashtag, it's a # and it stands for numbers. So make of all the variables and numbers you know. So if it mentions it in the problem, it says, oh, speed, you're like, okay, speed's a variable here. It affects things. 4, based on your variables, now you can pick an equation. You can say, oh, look, I'm using these variables. Wow, this equation has all those variables. That's the equation you want. And lastly, after you've picked that equation, solve it. Actually solve the problem, plug the numbers in. Alright, so go to page 21 in your large packet. You should see these 3 problems. Spend like about 10 or so minutes attempting them using the steps on the previous page. And then we'll go on to the answers. Alright, so coming back to this problem, looking at number 1, that would be this one. First step, Emily is running the 200 meter at a track meet. Alright, so I see some numbers here. I'm going to underline that. She starts from rest, okay. That tells us something about what she's doing, and accelerates with constant acceleration until she hits the finish line. If it takes her 24 seconds to finish the race, that sounds important, what was her acceleration? Alright, so that's the first step. Read and start underlining important information. So I may not have hit all the important information, I may have hit too much, but I underlined some things that I felt were going to be important to the problem. Next, draw and label. So okay, this is Emily. She's on a track. Try to give her a ponytail. She's on a track. She's running 200 meters to the finish line. She starts here. She's running, and let's see, runs, oops, not runs, and it takes her 24 seconds to get to the finish line. So I drew a picture, I labeled it, so it's a girl, she's running in a straight direction, and she finishes at the 200 meter mark. You can also think of, like, right here, her velocity, or her initial velocity, is equal to 0, because she is at rest, right? She's not moving. Alright, next step, we got to start looking at variables. So we can even look at the question at the end. It asks, what is her acceleration? So we know we care about acceleration. However, it's a question, what was, so we have no idea. Alright, we have to also look at, see where she started. Alright, she started at the start line, so we can call that 0. She started from rest, so her initial velocity is 0. Her time is 24 seconds. That's how long it took her to take the race. And her total change of position is she went to the 200-meter mark. Alright, that seems like all our variables. Now I'm going to erase our picture. Beautiful though Emily is, we gotta move on. Alright, so we have these variables, so go ahead and you can look at your equations, which you should have taken down last night from last night's notes. You can see, okay, I have a initial position, initial velocity. I don't have a final velocity. I have a final position, I have a time, and I have an acceleration. So hopefully you can look at your equations and be like, oh, this looks like this formula will do me good here, this formula. So x equals x naught plus v naught plus 1/2 at squared. So you'll notice we have everything except the a. So we want to isolate the a. We want to get it alone. But we know something about x naught and v naught. They're 0, so we don't care. It's not going to change our problem. So we can simplify to x equals 1/2 at squared. So again, you can do one of two things. You can just plug in your numbers now and solve for a. I like to solve for a first. If you like to plug in your numbers, that is also fine. So solve for a. I see, oh, a is multiplied against these two. So to undo it, I need to divide. Cross them out. Anything I do to one side, I must do to the other. So now to solve it, I'm going to go down to this area here. It's going to be a all by itself because we crossed out those next to it by dividing. And we keep this exactly as it is, x divided by 1/2 t squared. This is also the same thing as 2x over t squared, depending on how you want to write it. And now it's just a plug and chug. We know what x is. X is 200 meters. We know what t is. It's 24 seconds. Don't forget to square it. So you're going to get 200 meters over 24 seconds squared. Remember your squares you got to do first. So you'll get 24 seconds squared is 576 seconds squared. Remember, keep your units over 200. I'm going to erase some stuff because it's getting a little too crowded here. I'm just going to rewrite that a. So 200 divided by 576 seconds gives you 0.347, and keep your units. You see they're right here. Meters over seconds squared. Moving on to the next one. Alright, so number 2. Doing the first part. Nico is riding the BART to SF. If the BART starts from rest and accelerates at a constant rate at 10 meters per second squared, that's definitely going to be important, and the BART's top speed is 33 meters per second, how long does it take the BART to get to top speed? Alright, so I'm going to go back through it. So that's first step. Read the whole problem. So we're on BART. So BART starts from rest and does accelerate. So we're going to have acceleration here. And we have our acceleration right here. Alright, so now we have the problem. Now I'm going to draw a picture, okay? We have BART car here. It's going along the track. It starts from rest, so it's not moving. But it is going to accelerate. I'm just going to write it. It's going to accelerate in this direction. And at the end, it should be going 33 meters per second. That's our goal. It's going to start here, and then it's going to speed up and go 33 meters per second. So I kind of mentioned some variables we're talking about. Well, let's write them down. So we know it's the BART. She's apparently at a stop. So it starts from rest. So it stopped and then starts going. So that means our initial velocity, v naught, is going to be 0 meters per second. It's not moving. But it does accelerate. And our acceleration, the problem tells us, is 10 meters per second squared. Alright, and then we know that its final velocity, v, is going to be its top speed, 33 meters per second. Then the question is actually asking, we can see the question starts here, how long does it take Bart to get to top speed? So anytime it talks about how long, it's, what does how long mean? How long does your pasta take to cook? That's time. So our unknown here is time. So go look at your equations, figure out what equation would be good for this. Alright, hopefully you looked at your equation chart and saw something that looked a little like this. Velocity, final velocity equals v naught plus a t. You'll notice, oh wow, look, all those variables match. You do want to isolate t. So again, right now you can either plug in your numbers or you can isolate t first. I like to isolate t first, and I'm going to do so down here. So I want to get t all alone. First step, get the thing farthest away from it. That's this v naught. So you're going to subtract to both sides. So you're going to get velocity minus the initial velocity equals a times t. Since you're multiplied, you need to divide the a away. So you're going to get crosses out here. So you have v minus v naught over a is equal to t. Here's a nice thing. We can say, oh wait, v naught, oh that thing's just 0. We don't care. So your final equation is going to look something like v over a gives you t. And then you just need to plug your numbers in and solve it. We know what v is. It's 33 meters per second. Your acceleration is 10 meters per second squared. So you'll notice you're seeing some terms match up here. So you can say, oh, meters, second. Cross out the 2 because it's 1 second on top, 2 on bottom. There's still a second left. So you get 33 divided by 10. It gives you 3.3. You have a seconds left. Seconds for time. For those of you who are like, wait, it's on the bottom. Okay, think of it this way. We crossed out our meters, so it's 1 over a second. So it's on the bottom of the bottom, which means we can just put it to the top. Think of it like right now it's a fish out of water. That's a person underwater. It needs to go back to the surface where it belongs. Otherwise, we say, all right, that's our time. We found seconds. It's 3.3 seconds is our time. Moving on to the next one. All right, number 3, final one. Quang is skateboarding home. At t equals 10, he is 3 meters east of a stop sign and heading west at 4 meters per second. He sees one of his friends and tries to come to a stop decelerating at a rate of 1 meter per second squared. After 2 seconds, where is Quang relative to the stop sign? And B, at this point, is how fast he's moving. So this is essentially 2 problems. Do A and B completely separately. So let's go through and read this, okay? Well, let's draw a picture at first so we can figure out. So we have Quang on a skateboard. At the beginning, he is 3 meters east. So in case you're not sure, goes north, east, south. Never eat soggy waffles. Northeast, southwest. So he's 3 meters east of a stop sign heading west. So I actually need to change this picture, right? Because he's not on this side. He is on this side. So he's over east of a stop sign on a skateboard, heading west at 4 meters per second. Let's say here is our stop sign. Stop. And this is a distance of 3 meters. He's heading west. He sees one of his friends. So he's going to slow down a little bit, right? He's going to be slowing down, decelerating. Remember, that means that's going to be a negative acceleration. He's slowing down. So this is our picture. Now we're going to move on to, let's try to pull some variables out. So we're looking for ones that relate just to A. So after 2 seconds, t equals 2 seconds. Where is Quang relative to the stop sign? So we want to know his position. So we care that his initial position is 3 meters away from the stop sign. All right, we also know that he did have an initial velocity, which is 4 meters per second towards the stop sign. We want to know what's his final position. So where is he in relation to the stop sign? We also know his acceleration is a negative, because remember, it's deceleration. It is a negative acceleration at 1 meter per second squared. So looking at all these, hope you can say that, oh, it's going to be this equation. X equals x naught plus v naught plus 1/2 at squared. So it's actually already solved the right way. You already have x all alone. Good for you. It's easy. Plug in your numbers. All right, now we just need to solve. We have 3m. I'm going to change colors here so it gets less confusing. We have 3m plus, oops, I forgot my t variable in here, plus 4 meters per second times 2 seconds plus 1/2 the acceleration, which is -1 meters per second squared times time squared, which is 2. All right, let's simplify this a little. So 4, right, we see we have a seconds on top, seconds on bottom. 4 times 2 is 8 meters plus 3 meters. And we'll have 2 squared is 4. 4 times -1 is -4 times half is negative. Ooh, lost myself. -4, -1, -4. Half of that is -2. And if you notice, we got a 2 squared here, or s squared here, s squared here. So our seconds cancel out, and we're left again in meters, which makes sense. If you're adding, it should all be the same units. So now we have, and your teacher just realized you made a mistake. So in these problems, I'll admit, they're definitely trickier, because you need to designate like which side of this is positive and which side of this is negative. So I'm going to call, just like a coordinate plane, that east is positive and west is negative. So since he's traveling in the westward direction, we're going to call that he's going backwards towards the stop sign, essentially. And as far as acceleration, which direction is acceleration if he's decelerating? If he is going this direction, but now he's going that direction slower, he's accelerating in what I'd like to call the positive direction. If that's confusing, trust me, we will continue working on that. But what that means is we've got to switch some signs around. So you have to call one side of an object either positive or negative just to determine your relation to it. So since we called his being to the right a positive meters, that means him going to the left gives you a negative 4 meters per second still times 2 seconds times 1/2, and since he's technically accelerating by decelerating, you're going to give him a positive 1 meters per second squared times 2 seconds squared. So this term, oops, it's a plus sign, this term will still be 2 times 2, which is 4, times 1 is still 4, times 1/2 gives you 2 meters, plus this term becomes a negative 8 meters, plus a positive 3 meters. So add these all up. That 3 plus 2 gives you 5, minus 8 gives you a negative 3 meters. So what this means, as far as relation, at negative 3 meters, he's gone past the stop sign by 3 meters. So where is Quang relative to the stop sign? He's now 3 meters to the west. Alright, erasing all this and moving on to B. Alright, so we're still going to care about north, east, south, west, but not as much because we don't really care where he is at this point. We just want to know how fast is he moving at that point. So we don't care about where he is. We just want to know how fast he's going. So we got Quang still. He's still on the skateboard. He is going, again, don't care where he is, but he's going there at 4 meters per second. But he's slowing down at 1 meter per second squared. So now that we don't care where he is, we can call whichever direction we want positive. So to make things easier, him going whichever direction he's going is positive. He's slowing down, which is going to give you a negative acceleration. Or yes, negative acceleration. So we list out our variables. His initial velocity is 4 meters per second. His acceleration is a negative 1 meter per second squared, slowing down. And time equals 2 seconds. And we want to know what's his final velocity, or speed, in meters per second. So again, look up a formula. Hopefully you saw this formula would do it just so well for finding it. Everything's all laid out for you the way you want it. Now we get to plug our numbers in. V naught is 4 meters per second. That's his initial, plus negative 1 meters per second squared times the time, which is 2 seconds. Cross out one of those seconds. You get negative 2 meters per second minus 4 meters per second gives you 2 meters per second. So as always, check that your answer makes sense. Alright, he's going 2 meters per second. He was going 4, but he slowed down. So after time, it makes sense that he is now going at a slower pace. So your answer is 2 meters per second is our final velocity. Hopefully these helped you. We will continue working on this subject for some time, but remember to show your homework tomorrow.